Okay, so as part of our study of combined stresses, where we get the various normal and shear stresses resulting from simple loading conditions all happening at the same time, one of the first places that we're going to look at to demonstrate this is in thin wall pressure vessels. And it's a really easy space where we can see normal stresses going in both the x and the y direction at the same time. So it's a really great place to start. And so we're going to have to derive a couple formulas so we can figure out what the different stresses are occurring in these thin wall pressure vessels. So we see on this slide some examples of thin wall pressure vessels. There's a propane cylinder that we're very familiar with, whether it's for your barbecue, your fire table, air compressor or scuba tank. So there's lots of examples of thin wall pressure vessels. So what exactly are they? So they're vessels used for storage, typically of liquids or gases that are stored under pressure. And the inside pressure is greater than the ambient pressure, so they're pushing outwards, which pushes the pressure vessel into tension to contain that increased pressure inside. Now, from an efficiency perspective, we know that spherical is ideal. You're going to get the maximum efficiency as you can, but it also makes it somewhat difficult to contain or hold when the whole tank is round. And so we see a lot of other different shapes. So cylinders are also efficient, except for near the ends. And we see hybrids of cylinders and spheres and everything else. So we're only going to restrict our study to thin wall pressure vessels, which is to say that the radius is greater than 10 times the thickness. And this is a simplification that allows us to assume that we have a uniform average normal stress within the pressure wall itself. And so we can come up with fairly simple equations to reflect that. So we're going to start with spherical pressure vessels, and you see in the diagram up in the top an example of hemispherical or spherical pressure vessels on a liquid propane shipping or ship. And so we're going to look at how we can come up with a formula to figure out what the normal stresses are going to be in this case. And so here we are, we're going to start with our simplified sphere, and on the main part of the slide I'm going to show a hemisphere, because what we're going to do is we're going to take a cut and we're going to use our equilibrium equations along that cut plane, method of sections, in order to figure out what the normal stresses are. So we are restricting ourselves to thin walls, so our thickness to radius ratio less than 10%, and we know that the normal stress is the same in all directions due to symmetry, right? So we can put our differential element on. You see it up in the top right-hand corner there, where we're showing our sigmas in the two different directions, in the x and the y direction, if you will. And I've labeled them both as sigma 2, and that's just going to line up better when we look at normal stresses in cylinders. So we also know that the normal stress in the walls must be equal to the applied load, right? That's the basic equilibrium. So first off, we need to figure out what the applied load is. So pressure always acts normal to the plane and constant over its area. So we have this pressure, and we can see in this case, because of our cut plane the way it is, it's going to be acting to the left, constant P, over that entire surface area. So we can figure out what the forces have to be restricted or resisted by the pressure vessel itself. And so we know that we're going to have a normal stress in that wall acting opposite to the pressure. And so we see it going to the right, a magnitude of sigma, uniform over the entire area of the cut plane of the hemisphere. And so we're going to do a little bit of math. We're going to apply our sum of the forces in the x direction, set it equal to 0. And so if we look at the two sides of that equation, we have our pressure acting to the left, and it's acting over the entire area, which is, in this case, the area of the circle, so pi r squared. And we have our normal stress acting over the entire area of the pressure vessel itself, which is the circumference of the circle. So it's simplified down to 2 pi r, the circumference of the circle, multiplied by the thickness. And then we rearrange that and we can come up with an equation for the stress. The normal stress is equal to the pressure in the pressure vessel multiplied by the radius, all divided by 2 times the thickness of the pressure vessel itself. And that's it. That's for the spherical pressure vessels. We now have an equation that is going to allow us to figure it out. Now remember that that stress is acting both in the x and the y direction, equal in both directions. So now, if we look at cylindrical or near cylindrical pressure vessels, and we see an example of just a propane, industrial propane cylinder that you might have in a gas station or something like that. And what we want to do is to figure out, first off, what the stresses are going on in this cylinder. And we're going to start by looking at the hoop stress, or what we call the hoop stress, or the stress that's going around and binding it. And so here we simplify it down. We create a cylinder and we show sigma 1 and sigma 2. In this case, we don't have symmetry, so we don't know if they're going to be equal or not. And we're going to start by looking at sigma 1, or the hoop stress. So here I've taken a slice out of the cylinder, and it's a width dy. And we have the same restrictions as far as our radius and thickness and everything else. And take note of the axes that we're going to be using, the x, y, and z, just so we can refer to those. So we're going to consider equilibrium in the transverse x direction. So that is going to resist this pressure on this plane. And so we're, again, using the method of sections. We know that the pressure is acting orthogonal to the cut. And so we have the pressure trying to push this piece of the cylinder away from us in the negative x direction. And it has to be held in place by the stresses in the cylinder, which are going to resist it in the positive direction, coming back. Again, uniform over the material that's resisting it. And so if we do our equilibrium, in this case, sum of the forces in the x direction, set it equal to 0, we get 2 times, and so we look at the normal stresses in each end, if you will, of that little u. And so it's our value, sigma 1 is the magnitude, and the area of one of those ends is the thickness times the width dy. So we have 2 of those, so we get 2 times sigma 1 times t dy. And then from that we're going to subtract the pressure pushing in the negative x direction, and so we have our pressure times the area, which is the diameter, or 2 times the radius, multiplied by the width dy is the area over which the pressure is acting. And we set it equal to 0, and then we rearrange it, and we figure out that our hoop stress, sigma 1, is equal to our pressure times the radius, all divided by our thickness of the cylinder. And that gives us an equation for the hoop stress. So the only other stress we have left to fully define our cylinder is the longitudinal stress. And so we're going to do that now. And to get our longitudinal stress, I'm going to, very similar to the hemisphere, I'm going to take a chop across the cross-section of our cylinder, and we see it shown here on the slide, and we're going to see that this works out exactly the way it did when we did the hemisphere for the spherical pressure vessel. So again, we have our pressure across the area of the method of, or the section, and the resistance sigma 2 holding this half of the capsule, if you will, in place, going in the opposite direction. And again, in this case, we're going to consider equilibrium in the y direction, and we get sum of the forces y direction, set it equal to 0. So we have our sigma 2, or our longitudinal stress, multiplied by the area over which it applies, which would be our circumference of the circle, multiplied by the thickness of the cylinder, so 2 pi r times t. And then from that, we're going to subtract the pressure, or the force as a result of the pressure of trying to push the capsule away. So our pressure times the area over which it applies, which is pi r squared, or the area of the circle. Set it equal to 0, rearrange, and exactly like we got when we looked at the spherical pressure vessel. We get our longitudinal stress, in this case sigma 2, is equal to pressure times the radius divided by 2 times the thickness of the pressure vessel. So we just summarize it here. So stress is in a cylindrical vessel. So we have our hoop stress sigma 1 is equal to PR over T, and our longitudinal stress sigma 2 is equal to PR over 2T, and we know that both would be longitudinal stresses in the case of a spherical pressure vessel. So these are we know that the magnitude of the hoop stress is twice that of the longitudinal stress. So we have an example done up. I'll get the link and I'll add it to this slide. It's not here yet. And once I load up the video, again, I will add it here and I'll put it in a little note down below so you can follow that link. But it's a fairly simple calculation, just basically calculating the stresses in the spherical pressure vessel. And we throw in some safety factors and whatnot. And really that's here, it gives us a very quick example where we can get normal stresses in 2 different directions on a structure. And we're going to carry on now, and we're going to start to look at other types of loading and combining our simple loading. Remember, we have axial and torsion, and normal stresses due to bending, and shear stresses due to bending, transverse shear stresses due to bending. And we're going to start to combine those in different ways and look at how those stresses come together and start looking at principal stresses and some other ideas like that. But for now, this is pressure vessels. Gives us a quick opportunity to look at normal stresses going in different directions.